Okay, so we left off talking about the calorimeter, didn't we? So there's two types of calorimeters. Okay, there's the bomb calorimeter and the coffee cup calorimeter, right? Okay, do you remember the 3 steps that go with calorimetry? Step 1 is what? Table. Yeah, you got to set up the table, right? What's step 2? Put in those equations. Are you guys going to remember those equations? Yeah, because they will not be given to you, so you will need to remember those. And then what's the 3rd step? Units. Okay, that's going to be important because you're going to have to do a whole set of calculations just to get it in the right units, right? We're going to have to go from joules to kilojoules, and then we're going to have to divide it by the per mole of something. So to find moles, you might have to do molarity, okay, or use molar mass, right? Okay, so that was one way that we were determining the enthalpy of the reaction. There are 2 other ways that we're going to talk about. That's Hess's law and heats of formation. Okay, so those are the next ones. So Hess's law, I think is fun. It's fun. We'll see. Hess's law. I know this one is great, right? This one is. If you love puzzles, you'll like this one. I love puzzles, so. But Hess's law comes about because, remember our truths about enthalpy? Remember the truths about enthalpy? Enthalpy is, we said, extensive, so we did some stoichiometry with that. But we also said enthalpy is a state function. What's a state function? Remember that? It's independent of the pathway. Okay, so what does that mean? That means it doesn't matter how I get there. So if we're looking at this reaction, let's say I want to get to the final process. What's the enthalpy to get to those products? Well, I can go through reaction A. Okay, but what if I can't do reaction A? We can't do everything in a bomb calorimeter. So what if I can only do reaction B and C? That's okay. As long as I get from my starting point to my final product, it doesn't matter whether I go through reaction A or whether I go through reactions B and C. It's totally fine. It's the same thing, right? Because I'm starting in the same spot and I'm ending with the same spot. Okay, so I can add B and C together and get the same enthalpy as A. And that's what we're doing, is you're just going to add these enthalpies of these 2 reactions together. Okay, so we're going to add them together, and that will give us the same thing. So let's take a look at an example of that. All right, so let's have here's the Haber process again. So let's imagine that we don't know this value. Okay, so let's imagine that we don't know this value right here. All right, so how are we going to get this value? I have 2 equations that will give me my product. So we have to make sure these 2 equations give me the product that I want, and then I'm going to add the enthalpies together. Okay, so how do I do that? Well, I make sure that these add together to give me my target equation. So do you guys know how to add equations together? Have we done the add equations together? To add an equation together, I'm going to take all the reactants on one side and write them all together here. Then I'm going to draw an arrow and write all the products on this side. Okay, so and then when you do that, then we've done that before, right? Which is cancel out those things that are the same on both sides. So if I were to add all this together, I would say N2H4 plus H2 plus 2H2 plus N2, and then draw my arrow, and then I would have N2H4 plus 2NH3. Now right now that does not look like our target equation, does it? What we're trying to get is our target equation. It all has to match exactly. Enthalpy is extensive. It matters how much you have. It's got to match exactly. So let's see. Well, we've added them together, but does it match exactly? Let's see. What can I do? Well, for one thing, we can cancel out anything that's the same on both sides. Do you see anything that's the same on both sides? N2H4 is the same on both sides? Okay, so I can cancel that out. Anything else? Okay, so nothing else cancels out, but what about this? Can I clean this up a little bit? I've got 1 here and 2 here. Can I add that together? Yes, I can. So that'll be 3H2 plus N2 gives me 2NH3. Now, is this the same as my target equation? It is. It has to match exactly. And then I'll add them up to double check, and yes, it does. So if this matches my target exactly, then can I just add those 2 enthalpies together? Yes. So if I add these 2 enthalpies together, it'll give me my target equation enthalpy, and that's what I want. And if we add those together, then that is what we get. Okay? So that's how we're going to do Hess's reaction, is you add the equations together. Now, when you're canceling things out, notice that we canceled out something that was produced but wasn't in the target equations. Okay, so this is what we call an intermediate. It was produced but then used in the next step. So it doesn't appear in the target equation. It does cancel out. Okay? All right, so that's all we have to do is just simply add them together. That's Hess's law. Now, if you were to add something together, let's say we had an equation that had 5O2, an arrow something plus 5O2 is 3O2 plus something something. Do you see how I can cancel the 5O2 and the 3O2? How can I do that? Cancel what? 3 of these and then what? Leave 2 of those behind, right? Okay, so that's how we can cancel out. And that's it. That's what we're doing. We're making sure they add together to give us our target equation and then add the enthalpies. Yay! Okay, but what happens if those 2 target equations, here's the fun part, don't quite add up to give us our target equation? Then what should we do? Well, we're going to have to do something to those target equations. We're going to have to change them somehow. Okay, so how do we change those step reactions? Well, we can only do 2 things. Okay, it's kind of like puzzle pieces. If you like puzzles, right? It's like, oh, we're trying to put the picture together, right? And you have to take those puzzle pieces and you have to turn them around until they fit. Well, you're going to have to turn these around until they fit. Okay, so that's what we're going to do. And what can we do to the target equations? Only 2 things. You can either multiply or divide, okay, or flip them. Now, do you remember we talked about the truths of enthalpy? Because that's what we're using. When we multiply by a number, what are you supposed to do to the enthalpy? Multiply by that number, right? Because isn't enthalpy extensive? It matters how much you have. So if I've multiplied all the coefficients by a number, then I'm going to have to multiply the enthalpy by that number. Well, what if I divided all the coefficients by 2? What would I have to do to the enthalpy? Divide it by 2, right? Okay, so that's one thing you can do. Another thing that you can do is to flip the reaction. Do you remember what I said when we flip the reaction? What's that? Yeah, reactants on the other side, because aren't we like what? Reversing it? Doesn't that, remember we talked about flipping it as reversing it? What happens to the enthalpy when we reverse the reaction? Change the sign. That's right. So you got to remember to do those things. Those are the truths we learned about enthalpy. So you can take one of those step reactions, you can multiply, and maybe you'll have to flip it. You might have to do both things to it. You might have to do nothing to it. You might only have to do one thing to it. Okay, so that's what we have to figure out, is what do I have to do to make those match the target equation? Maybe nothing, maybe both things, maybe only one thing, maybe just flipping it, maybe just multiplying it, maybe do both. Okay, does that make sense? All right, and then once you get that to add together to give us our target equation, then we add them together. You just add them together, cancel out what doesn't belong in there, and there's your enthalpy. So let's practice this one. There's our target. So what you're looking at is you want to look at your target equation. That's what you want to match. We cannot change the target equation. So the things that we can do only can be done to the step reactions. Okay? So can we ever change the target equation? No. Okay, you guys remember that? Never change the target equation. Which ones can you change? The step ones, right? Does everybody understand that? We can only change the step ones. That make sense? You're never going to change the target equation. You're only going to change the step reactions. Well, how can we figure out how to change it? Well, what we're going to do is we're going to match it up. Okay, we're just going to be like, ooh, match game. Find it, find it. Okay, so let's start with the first 4 aluminum, and it's a solid. So we're going to start there. Remember, enthalpy is extensive, so I better make sure I have 4 of them. 4 aluminum, and then we want it as a reactant. Okay, so there's the first thing we're looking for 4 aluminum. So the next thing we want to look at is in our step reactions. Hey, where do we see 4 aluminum? Anybody see 4 aluminum? Can you find it? Yeah, does everybody find it? Where do you find it? Product where? In the step reactions in the first one, right? Because we're trying to match this. So this is like your plan. Okay, so there's a 4 aluminum. So we're looking for it in here in these step reactions. There it is. Now, is it 4? Yeah, okay, that's good. How about, is it a reactant? No. What can we do to change it to make it be a reactant? Flip it. So I flip that one, but if I flip that step, what happens to the enthalpy? Change the sign. Okay, so let's write that down. So, because once you do that, then we've changed the step equation. All right, so let's write that down. 4 aluminum, I'm just going to reverse it. 4 aluminum plus 3 O2 will give us 2 Al2O3. And don't forget to change the enthalpy. We always have to remember that. That's a minus 3352 kilojoules. Don't forget to change that. Now, once you've done something to an equation, you have to cross out the old one. You can only look at the new one that you just did now. Okay, so now we're looking at this one and that other one on the board. So we did 4 aluminum. Now we're going on to the next thing. 3 MnO2. That's what we want. That's our goal. Now look for it. Do you see anything here or on the board for 3 MnO2? Can you find it? It's like, ooh, hide and seek. Where is it? Where is it? Where is it? Second equation or first equation? Step equation. This one or that one? Where is it? This one? Is it a reactant? Is it right here? Yeah. Is it a reactant? Yes. Does that match that reactant? Okay, except, what about the, how much? 3. I need 3. Does this have a 3? No, it's got to match exactly. Okay, that has 3 MnO2 as a reactant. Guess what? That better be what? 3 MnO2 as a reactant. It's not. What should we do? Multiply everything by 3? Okay, so let's do that. So 3 MnO2. Don't forget to do everything by 3. 3 Mn plus 3 O2. And then what should I do to the enthalpy? I have to multiply that by 3, right? Okay, so it's, what? How much is it? 1560. Okay, so let's write that down. 1560. Okay, there it is, 1560. Okay, so now I'm not looking at that one anymore. I'm looking at these two because I've changed it. These are my 2 new step reactions. So let's keep going. We need 2 Al2O3 as a product. That's my next thing I'm looking at. So look over here. Can you find it? Can you find it? Where is it? It's right there, is it? Do I have to do anything to it? No, we're good. Yay! Okay, what about the next one? 3 Mn. Okay, let's find it. Right there? Do I have to do anything? No. Yay, we're done. Okay, see how fun that is? We're just like, yeah, we look and then we find it. And then when we add these together, we do get our target equation. We've canceled out what doesn't belong. And then we need to add these together to give us what our final enthalpy is. So when we add these together and cancel out what doesn't belong, we will get 4 aluminum plus 3 MnO2. See, 2 Al2O3, 3 Mn. And then you add these together, right? And we get 1792 kilojoules.
So we don't have to flip the second one?
Not this problem. Maybe another problem you might. Not today on this one. Different problem you might. It just depends on the equation. Okay? Does that make sense? All right. Okay, do this one. Now I do want to point out to you that the calcium 2 plus is not the same thing as the calcium solid. Can I cancel these out? No, because this is an ion, right? And that is not. They don't cancel. Same thing with the H plus, okay, and the H2. You can't do that. They're not the same thing. So when you copy and write these down, you can't drop off that 2 plus. If you do, it's going to be a problem for you. Okay, so see if you can solve that one. Okay, you're starting with the first one, right? You're looking for this one? Where is this one?
This one has 2 on it.
So what are you going to do?
Divide it?
So did you do that?
Okay.
And then write down the new reaction.
Okay.
And cross out the old one, right? You're working with this one first, aren't you?
Mm-hmm.
Okay, where's this one? Look down here. Can you find it somewhere? Where is it? Where is it? There. Does it match exactly?
No.
So what do you have to do?
Add 2 to the...
You can never change the target equation. You can only change the step. Never change this. So how are you going to make this calcium match that calcium? Yeah, and do what with it? If this is 1 calcium and that's 2 calcium, what do I do to make this be 1 calcium? By 2 divided by 1 is still 2. What am I going to divide by? 2. So divide everything by 2, right, including the enthalpy? Okay, so write the new one down. So you start here. Don't start with these. Start here and find it. It's like, where is it? It's like hide and seek. Can you find it? And then do something to it. Okay? Did you get it? Let me see if that's the right one. Did you get it? Okay, that should be negative 431. What did you do? You divided everything by 2, yeah? And you crossed off the old one when you did that?
Because I reversed this one.
Okay, so now try it again. Okay. Okay, yeah, you always have to do the enthalpy, right? Okay, how are we doing?
I
Are we
am trying to
focusing?
survive this week.
You focus on what we're doing, yeah? Uh-huh.
Yeah.
Yeah, you should try it.
This is long.
Yeah, you
This was
should.
cool.
Uh-huh.
Puzzles.
Mm-hmm. Okay, you did this one?
Yeah.
Okay, so you got that one. Now you're looking for this one, 2H2O. Where would that be?
I'm working on it right now.
So where is it? Can you find it? Where's the H2O? And the first, where are we looking for? Oh, there it is right there? Okay, good. Now, is it matching this exactly? No. So what are you going to do to this? Multiply everything by 2, right? But I also have to flip it, don't I? Doesn't it have to be a reactant? Okay, so multiply by 2 and then flip it, right? Okay, and then that'll be your new, don't forget to do that to the enthalpy, right?
But did you have an A in it?
Yeah.
So you don't need an update on your grade?
How are you guys doing? Did you get it?
Cleanest.
Good, good. All right. Okay, looks like we got it. So, okay, so what did you have to do to these equations? What did you do to this one? What did you guys do with this one? You divided it by 2? Yeah. And you divided by 2, right? You remember to divide that by 2? Uh-huh. So what did you do to this one? So everybody flipped it and multiplied it by 2, didn't you? Okay, so when you do that, what is the answer? That's exactly what we needed to do. And what's your answer do we get? Negative 431.2. Okay? So you guys got that? Negative 431.2? Okay, awesome. If we had trouble, you might want to just write that down and practice that later today, right? Minus 431.2. Okay, questions about that one? We got it? Okay, so let's talk about the third way, and that's with heats of formation at standard conditions. Now, we know that enthalpy changes, right? We know that with states and things like that. We're going to define a standard set of conditions, enthalpy under a standard set of conditions. Okay, enthalpy, and we're going to say standard state. Just like we had standard temperature and pressure, we're going to have standard state conditions. That little symbol means standard state. Now, what are the standard conditions? Pretty much where we are right now in here, which would be 1 atmosphere, since we're pretty much at 1 atmosphere, and room temperature. Okay, and the other part is 1 mole. Okay, so these are the standard conditions, because enthalpy matters how much you have, so we have to specify the amount. And we know pressure and temperature can change the state, so we're going to specify the pressure and the temperature. Pressure is 1 atmosphere, room temperature, okay, and 1 mole. Those are the standard conditions. Now we're also going to talk about another thing, and that's called formation. That's the enthalpy of formation. Now this is a huge table. You have all these substances in the back of your textbook. It's a very large table. This is only just a little piece of it. Okay, so on the exam, we're just going to give you what little snippet part of the table you need. We won't give you the whole table that goes multiple pages. So you have all these substances listed. So we can classify these substances as either elements or compounds. So let's start with the elements. Now if you look at the elements, some elements are 0 and some are not. Okay, we have to know which elements have a heat of formation of 0.
Gases.
Okay, gases would be 1, but depends on an elements. Okay, so that's right. So what we're going to do is we're going to think of which elements have a heat of formation of 0. Some do, some don't. So what we're going to say is, how do we know? We know because whatever they exist as in these standard state conditions will have a heat of 0. For example, let's talk about oxygen. How does oxygen exist right now, right here in this room? It's diatomic. What else do you know about it? It's a gas, right? It's a diatomic gas. Okay, so a diatomic gas is how O2 exists. So O2 gas is going to have a heat of formation of 0. What about O2 solid? Will that have a heat formation of 0? No, because you have to do something to it to get it to turn to a solid, right? Or O2 liquid. I'm going to have to do something, cool it down to get it to be a liquid. All right, so O2 gas has a heat of formation of 0. Not O2 liquid, not O2 solid. How about oxygen as the monatomic gas, right? It comes as O2, so I'm going to have to do something to break it. So just oxygen all by itself without being diatomic also has a heat of formation. Does that make sense? So now if we think about, we've already talked all about the diatomics, we've talked about the states. So do you remember that there's 2 liquids on the periodic table that exist like as liquids, room temperature, 1 atmosphere, bromine and mercury. Bromine and mercury. Okay, so mercury, what's going to have a heat of formation of 0? Mercury liquid or mercury solid? Mercury liquid. You see how that works? Because we know that. Now we've already talked about the noble gases. They're going to be what? Gases. So they're going to have a heat of formation of 0. Some of the diatomics, do you remember which ones are gases? Yeah, all of them except for bromine is the liquid. And what about iodine? Does everybody know iodine's the only diatomic that's solid? Okay. So those elements have a heat of formation of 0. We do need to know which elements have a heat of formation of 0, but we kind of already knew that. We already had talked about that. All right, so example, let's take a look at this one. Which one has a heat of formation of 0, magnesium solid or magnesium gas? Magnesium solid? How do you know?
Because it's in solid state normally.
Yeah, because under these conditions, magnesium exists as a solid. We know that, right? Okay. So the heats of formation of any of the elements that are in standard state, we all can pick those out and know those are 0, right? So we're not going to give you those heats of formations because you already know which ones are going to be 0. Okay, so those are not given to you. So we do need to know which elements under what, state and all of that has a heat of formation of 0. Okay, well, what about the compounds? Because the compounds do have heats of formation. Because we're going to start with the basic elements. So if I have basic elements and I want to make a compound, I'm going to have a reaction. And that reaction is going to involve an enthalpy change. So anytime I have a compound, there's an enthalpy change involved with it. So a heat of formation for our compound, but remember we're at standard conditions. Okay, so we have to make sure we're following certain conditions. Now we can represent that formation of this compound by an equation, but in that equation I can only have 1 mole of the product, not 2, not 3, not a half, 1 mole of the product, and the elements are what I'm going to use as reactants. I can't use any compounds, I have to use elements. But which kinds of elements as reactants? Those that have what? A heat of formation of 0. Yes. So I can't just use any elements, I have to use those elements that have a heat of formation of 0. So we need to know which ones those are, right? Okay. And when I have these two conditions, 1 mole of product and elements as reactants with a heat of formation of 0, you still have to balance this reaction. So let's take a look at this example. I have elements that have a heat of formation of 0 because sodium is a solid, that's a heat of formation of 0. Chlorine, diatomic gas, okay, so that one has a heat of formation of 0. And I only can have 1 mole of the product. But if I have 1 mole of the product, I still have to balance it. So, whoa, what do I have to have in front of the chlorine then? What's my coefficient for the chlorine? What's the coefficient for chlorine? A half? Do we usually have fractions for coefficients? No, but in this case we do, okay? So this is the time that you'll see fractions as the coefficients because, why do we have fractions as the coefficient? Because how much product can you always ever have?
1 mole.
1 mole. So that means you might have to have fractions to help you balance the equation for that. Okay, so those are the conditions. So let's see. Looking at these equations, can you tell me which one of these equations represents the heat of formation reaction of the compound? Now, do you remember what our conditions were? How much product can we have? 1 mole. And what about the reactants? What can you tell me the reactants have to be? They have to have a heat of formation of 0. And can they be compounds or do they have to be elements? Elements, because compounds don't have a heat of formation of 0, right? So they're going to have to be elements. Okay, so I want you to think of which one of these is a heat of formation reaction and which one of these is just an ordinary combination reaction. Okay, so I want you to think about it. Take a minute and decide, yes, it's an example of a heat of formation reaction, or no, it's not. Remembering our two conditions. Okay, so think about each one. It's either yes it is or no it isn't. Okay, did you think about it? Did you make your decisions? Okay, now check with your neighbor and see if you were right. You should have the same answers. All right, so what did we think? Did all our answers were matched up, right? Everybody got the same answers? Yeah? So what do you think? First and last? Last, second, and third? What? Are they all yes? They all no? I don't know. Let's take the first one. We'll go through them one at a time. What's the answer for the first one? It is an example of the heat of formation, or it is not? It is? Does anybody think it's not? Okay, it's not. Oh, now why? Okay, we have to have, what did we say for the product? You have to have 1 mole as a product. We got that. Now, what did we say about the reactants? Must be stable? Okay, well, carbon solid, graphite, that's stable. Yeah, it's true. Carbon, not diamond, right? Everybody knows diamond would not be the most stable form, right? Carbon, graphite is the most stable. Okay, that is. But what about the hydrogen? What should it be? Diatomic. True, it's a gas. That's all fine and good. But is it a diatomic? No, it is not a diatomic. So, that first one, this is the problem. So that is not an example of a heat of formation reaction then, is it? Okay, what about the second one? What did we say? We said it was... It is or it is not? Okay, I hear some yeses and some no's. Why do we think? Is not? Why not? It's what? 2 moles of NH3. You can't have 2 moles of product, can you? No, you can only have 1 mole of product. So that's the problem with that one. So that one's not it either, because you cannot have 2 moles of product. Right? Whoops. Can't have that one. Okay, what about the third one?
It has to be elements.
Okay, it has to be elements, right? Did we say that? Do I have 1 mole of product, by the way? Okay, that part's good. Now let's take a look at the elements. Am I supposed to have elements as reactants? Yeah, do I have elements in their most stable state? No. So is that a heat of formation reaction? No. Does everybody see why it's not? Can you have a compound as a reactant? No. What do you have to have? An element. Is C2H6 an element? No, that's a compound. Okay, so is that why that is not a heat of formation reaction? All right, well, let's look about the last one. Gosh, any of these ones? How about the last one? It is? Why is it? Okay, so we have 1 mole of product. Chlorine, yep, that's in its most stable state, right? Diatomic gas. And then potassium solid, most stable state, right? So does everybody see why this one, this very last one, yes, this one is? Yes, it is. Yay! Boink. Okay. All right, does that make sense? So now you can tell me which elements have a heat of formation of 0, can't you? And we needed to know that in order to answer the question of How did we get the heat of formation for the compound? Because you have to have elements as heat of formation of zeros reactants, right? Okay, so we've talked about the elements and we talked about the compounds with heats of formation. Are we okay with that? Everybody understand those things? Okay, well great. Now what are we going to do with them? Now that we have all these heats of formation, that big old long list of that table, what can we do with them? Stoichiometry. I know you're thinking, yes. Well, we can use them to calculate enthalpy in another way, but this way is easy. This way is easy. Now, we want the change in enthalpy. Now, we can use those heats of formation, and we can calculate any reaction we want, any reaction that we want under standard conditions, of course, but any reaction. So how do we do that? Well, the change, how do you find the change? We said change is always defined as what? Final minus initial. Well, that's another way of saying final would be what? Products minus reactants. So that's what you're doing, is you're summing up all the products. Okay, so does anybody know what that little symbol right here means? You guys know this one? It means sum up. It means add up. So you add up all the reactants. You add up all the products. Okay, now these, M and N, okay, those represent coefficients because enthalpy is extensive. Doesn't it matter how much you have? And so we are talking about per mole. So if I have 3 moles, because I have a coefficient of 3, don't I need to multiply that enthalpy by 3? So what we're going to do is we're going to multiply what your number you're getting from the table by the coefficient. Because in the table we're talking about 1 mole. So if I have 2 moles, I got to multiply it by 2. If I have 3 moles, I got to multiply it by 3. And then you just add them all up and subtract them. I think the biggest thing you have to watch out for is the minus sign here. Remember to add all these up before you subtract it from all of those added up. And always start with products. Don't start with reactants. That's another common mistake. All right, so let's take a look at an example of that one. Okay, so here we have our reaction. Okay, so let's do products. Remember, products are first. So we have to do the products first. So I would go to the table and I would look up the products. And I would look up CO2, but you have to be careful. Is it CO2 gas? Or CO2 solid? Or CO2 liquid? What am I looking up? Gas. Okay, so watch that carefully. And when I get that number from the table, do I have to multiply it by something? Multiply it by 4. Does everybody see that? I would multiply that by 4. So I look it up in the table and it's minus 393.5. I didn't write kilojoules per mole in there, but that's what it is. And you multiplying it, you can think of it as by 4 moles. So the units, moles will cancel out and I'm left with kilojoules. All right, so let's keep going. The next one is water. Okay, so I have to look up water. You have to be careful. You can't look up solid or gas. It has to be with the liquid. So I do that one, and I multiply that by what? Multiply it by 2, right? And it's a negative number, so watch the signs. Okay, so there's all my products. Be careful, some of them are negative numbers. Minus, and then I'm going to do the reactants. Okay, so the reactants would be C2H2, so I have to look that one up. And I'd have to multiply that by 2. Now that's a positive number, so you be careful. Plus 5, what would O2 gas be? 0. Does everybody remember that's 0? 5 times 0. Okay, now watch the math carefully. When you do that, this is what you get. All right, so we see how we do that? That one's easy, right? So of the 3, which did you like? Calorimetry, Hess's law, or heats of formation? Heats of formation! I always like Hess's law. Didn't you think that one was fun? No. All right. So do you know what to do with heats of formation? Yes. Which you do products minus reactants, right? Not the other way around? Okay. Everybody got that one? And then we look up the values in the table. Don't forget to multiply it by a coefficient. All right. Does that make sense? Okay, so if you have your textbooks or access to an ebook, then let's do another problem. So see if you can do this one. Okay, so let's do the next one. Okay, see if you can add that one up. Okay, is that equation going to be given to you, by the way?
Yeah.
Nope. You're going to remember that, right? But we will give you the table. You guys can remember products minus reactants, right? That's like final minus initial. We know that. Okay, and you do have to have the data from the table.
Is it in the back of the book?
Yeah, it's in the very back of the book. It's a big, long table. Let's see, where is it? Okay, it's appendix C on page 1100. So flip to page 1100. Take a look at those numbers. So it's a lot. It's a double column table, so you're going to have to look at both sides there. Yeah, look at those numbers. Look it up, and it goes pages and pages. And if you're in the 12th edition, it's on page 1059 in the 12th edition, or the 13th edition, it's the 1100. If you're in the 12th edition, it's 1059. Okay, so look them all up. So we're doing, yeah. So where are you going to start with, reactants or products, by the way? So which one are you going to look up first?
NO2.
Well, you know what? That's which one? That one. That's really not a product. Remember, you said you told me products. That's what you're looking over here. You told me products. You know what that is? That's going to have a heat of formation of 0 because it's a diatomic gas. So you already know that. So that's 0 there. And then you have to look up this one. Okay, water actually is under oxygen.
Oh, it is.
Yeah. So let's see. See, it's under oxygen. Okay, so to find water, look under oxygen. No, it's 1,000. What's that?
From the previous problem.
Oh, yeah, that's right. That's right. We do. Oh, this is an older edition. Huh?
This is 13.
Let's see. It's usually...
Are on the table in the kilojoules or just joules?
It's in kilojoules.
Oh, okay. Thank you.
It's 2 columns.
Thanks.
So you're going to do products first, right? Okay, products. Yeah, 0, and then that one. Okay, so now do the reactants. It's not plus. Remember, it's final minus initial, so that's a minus. Okay, now look up these two. Well, you know that one already, too. That one you should know. We'll look up the other one. It's the gas. Make sure you get the one with the gas. Yeah. Yep, that one right there. Don't forget to multiply it by any coefficients. Did you multiply by coefficients? Okay, good. Okay, do we find those numbers? Okay, put them in.
I'm sorry.
Okay.
Oh,
All
I
right.
was gonna ask you, is it okay if I take the exam, the third exam, instead of Saturday, because I have holidays on Friday? Monday. I'll do my best to take it on Monday.
So how we doing? Good? Maria, you got it? Oh. Do you know how to do it though, yeah? Where did you find it on page, was that the 12th edition or 13th?
This is the 13th.
So it should be on page 1100.
I went past it and back.
The very end of the book, yeah? 1100? Whoa, there you
Oh,
go,
wait.
right there.
Oh, finally. You're later. Now that everyone's done. Alright.
Well, you know some of these heats of formation already. You know that should be 0, and that one's 0. So you only need that number and that number. And then she's got those numbers. So.
What happened to your foot?
There's the gas and there's
Okay, did we find all the numbers? And we looked them all up and we did the math, right? Okay, so how's it looking? All right, what are we getting for our answer? So it's a minus, right? You said minus 976.94. Perfect. Everybody got that? And what were the units, by the way? Kilojoules. Yay! Okay, awesome. All right, that's heats of formation. So we've talked about the 3 ways that we find the enthalpy of the reaction.